Hi, welcome back to AP Physics 1, Unit 5, Linear Momentum. So in this video, we're going to look at conservation of momentum. So we're going to start shifting from impulse momentum theorem to now one of those conserved quantities mechanics, of which momentum is the second one, right? So the first one was back in Unit 4, which was energy. So here in Unit 5, we're talking about momentum, right? And then in Unit 7, we will talk about angular momentum. Okay, so first thing. So like energy, momentum is a conserved quantity, right? And we just talked about how there's 3 of them here in mechanics. Now, if the total force is 0, then the initial and final momentums must be the same, right? So that's our caveat with all these conserved quantities, that we, in the absence of a net external force, in an isolated system, which means energy and mass aren't going in and out, right? This is the statement for the law of conservation of momentum. Now, what we say is only external forces can change a system's momentum, while internal forces have no effect on a system's momentum. Okay, so easy way to think about that is not necessarily like an example with momentum, but if we just think about it in terms of energy or so forth. So I have an object falling, right? Let's say in the first scenario, the system is the Earth and the object. So what happens is the weight, which is the force of gravity from the Earth, becomes internal, which means then all those quantities up above will be conserved. Okay. Now, in the second scenario, let's just call the object the system. So really what happens is this force vector extends out of the system, which means now, orange, sorry, this weight becomes external, right? Thus changing all those quantities above, right? The energy will change, the momentum will change, and if it's a spinning object, the angular momentum will change. Okay. Now, in fact, momentum is conserved for all systems. Doesn't matter what kind of system it is, but it is conserved for all systems to include the universe. And then for this video, the big application of conservation of momentum is recoil, right? So recoil, right, is the backwards motion of an object. Okay. Now, here's how the conservation of momentum works, right? And so this will be applied over the next couple videos when we look at here with recoil and then the 2 types of collisions and then ultimately ending up at ballistic pendulums. So, right, here is the key statement. The total force is 0. The initial and final momentums must be the same. So what they're saying is if I take the sum of all the momentums before a collision or before an action, that has to equal, right, the sum of the momentum after. Now, you may see it written something like this, right? Delta P equals 0, right? So that just, if I kind of solve that out, that just, ends up looking something like that up there. So when I sum let's say I have 2 objects in a system. So the mass of object 1 initial times the velocity initial, right? So the momentum of 1 plus the momentum of 2 initially has to equal the momentum of 1 after plus the momentum of 2 after. Okay? Now, the situation of recoil. Typically in recoil, the objects are not moving before the action happens, right? And we'll talk about a couple examples here in a second. So you have M2 V2, M1 V1 final plus M2 V2 final. And so typically, although it's not on this practice problem, but typically you're going to be looking for one of the velocities after, right? In the practice problem that we're going to go over, we're actually looking for one of the masses. So if I'm looking for the velocity after, I'm going to do negative m1 v1 final over the second mass, right? And so that would be your recoil equation, right? So recoil speed. Okay, two practical examples. One is this ballistocardiography, right? Ballistocardiography. So it's another way to read a heartbeat, right? You have EKGs, but then you have this here, which is they call a BCG, right? Ballistocardiograph. And what it does is there's a little sensor under a bed, and actually that sensor picks up the recoil, right, of the heart, and is able to transmit it back to beats per second, beats per minute, right? The other practical example is that you see is oftentimes is why did they put wheels on cannons? Okay, this seems like it's a no-brainer, right? So cannonball goes flying out the front of the cannon. We all know from movies and such the cannon. Let me get a different color, right? The cannon is going to go backwards, right? It's going to recoil back. Well, in the old days, without the wheels, right, the cannon would flip up, and that's a pretty heavy object coming at the cannoneers, the bombardiers there, whatever you want to call them, right? And so what happens that with the wheels are able to roll back to dissipate the energy, right? Because it's got to go somewhere, right? Instead of it flipping the cannon backwards, it rolls backwards, okay? So let's look at an example problem. And again, this will typically be the equation you use, but in this example, we're going to solve for the mass of a second object, okay? And in fact, it'll be a second ice skater. So two ice skaters stand at rest in the center of an ice rink. When they push off against each other, the 45-kilogram skater requires a speed of 0.62 meters per second. And then if the speed of the other skater is 0.89 meters per second, what is that skater's mass? So if I just draw my people as blocks, right? Before the quote unquote explosion, and oftentimes these recoil problems, we will call them explosion problems, right? It's not because there's a lot of actual fireworks and stuff going off, but the action simulates that. Nothing's moving to start, something happens in the system, and then they go off together, right? So before, V1 initial is going to equal V2 initial, which equals 0. Okay? Then after, not the highlighter, after the push off, one goes one way, one goes the other way, which means if this is my V1 final, this has to be negative, and this is my V2 final, and that's going to be positive. Okay? So here's my after. But let's go through the problem solving process. That's the picture. So the sum of the momentum before is going to equal the sum of the momentum after. And so it's going to be, we know the sum of the momentum is going to be 0. And it's going to be M1 V1 final plus M2 V2 final. Now again, in the previous slide, we solved it for V2, right? V2 final. But in this slide, we're going to solve it for M2. And so we're going to say M2 equals negative M1 V1 final over V2 final. So I want to point out this negative sign is from the solving, and you'll see that we'll plug in a negative sign for V1 final because this is the person who's going backwards. So negative, the mass of the, so negative 45 times negative 0.62 divided by 0.89. Again, this negative is because this person is going backwards. Okay? They're going in the negative direction. So the mass of the second person will be 31.3 kilograms. Okay? Another way you can think of it is, right, that your momentum of object 1 has to equal your momentum of object 2, right? And so what happens is object 1 is a big M, little v, right? And here I have a bigger v, which means that my mass I know has to be smaller than my the initial skate or the other skater, right? Because they're bigger, right? They're bigger with a slower speed, and then my second person has a faster speed, which means they have to be smaller. Okay. So the next couple of videos, again, we're going to keep applying this conservation of momentum. Here we're just looking at these quote-unquote explosion problems. Next, we're going to start talking about different types of collisions.